Hi everyone, welcome to this session. My name is Junye Huang. I'm a quantum developer advocate from IBM Quantum based in Singapore. So today I'm going to talk to you about towards quantum advantage in the financial services sector. So first is a little bit about me, my background. So as I told you, I'm a quantum developer advocate. My focus is on quantum education. I teach people how to program on quantum computer and using our open source quantum software Qiskit, which I'm going to tell you about today. And also leads the Qiskit Advocate program, which supports the most active member of the Qiskit community through organizing events, networking, and we also have some mentorship program. And earlier this year, I led a team of more than 40 people for IBM Quantum Challenge 2021 in May, which was an online quantum programming challenge event, lasted about 7 days. And that was a celebration of the 5th anniversary for IBM Quantum. And also it's the 5th year we put the quantum computer on the cloud for everyone to use. And coincidentally, it was also 40 years of quantum computing, marking from the 1981 when Richard Feynman talked about quantum computing, bringing the idea of quantum computing in a joint conference organized by IBM and MIT. And because of last year, I supported a Qiskit Global Summer School 2020, which was the biggest ever online quantum summer school with more than 4,000 students. And I received outstanding accomplishment, which is the highest level of recognition from IBM research. And I also like making games. And because I do quantum computing, I love quantum computers. I make games for quantum computers, such as a few names I show you, Coupon, and you can see the GIF on the right, bottom right corner. And before joining IBM, I was a graduate student and I studied topological quantum computation. That's why you see on my right the photo of me doing experiment on a dilution refrigerator, which what most people think when they look at this fridge is the computer, but actually a computer chip is at the bottom of the machine. The whole thing is just to cool down the chip to a very low temperature so that we can have a very low thermal noise and shield it from the environment to make sure the quantum computation can last for longer. And as you can see from my background that I'm not an expert in finance at all, but I do know a little bit about quantum computing. So I hope that today you can learn something about quantum computing, and I hope to learn things about finance from you. So if you have any question, you can post on the Slido, and then I will monitor and I'll try to answer at the end of my session. So this is the outline of today's talk. So we have 3 parts. The first part is to give you an introduction to quantum computing, because I know that people on the audience coming from very diverse background, so you may not know that much about quantum computing. So I want to spend a little bit of time to just give a very quick introduction and also do a demo for you to show you how now using IBM Quantum, you can already create accounts, run some simple quantum program on real quantum computers. And the part 2 is about application in finance using quantum computers, which is where all of you are tuning in to listen to today. And then part 3 is to tell you a little bit about the current technical challenges and what we think that we will need to improve on before we can really achieve a quantum advantage using quantum computers to solve problems in finance sectors. And also we'll show you a roadmap in IBM Quantum, how we plan to tackle all these challenges and scale up the quantum computers, improving them, and hopefully demonstrate quantum advantage in the next few years. So let's dive right into part 1, introduction to quantum computing. So it's a good way to understand quantum computing is to see the analogy comparing to a classical computer for quantum computer. So for a classical computer, the most fundamental unit of information is a bit. And you can easily understand it as like a switch, like showing on the slide. So a classical bit can only be 0 or 1, like a switch can only be on or off. So they are discrete and they can only be a deterministic state. While a quantum computer, the most basic unit of information is called quantum bit or qubit. And a qubit can be represented by this a sphere, or you can think about it on Earth. And so every point, every state of the qubit can be represented by a vector here. Or if you're on Earth, it would be like some point on the surface of Earth. And this means that in the north pole of this sphere is 0 state, same as the classical bit, and the south pole is 1 state. And then for classical computer, it can only be 0 or 1, but for classical computer, quantum computer, it can be anything in between. So you might have heard about the things about Schrödinger's cat, that it can be dead or alive at the same time. So this is really showing the quantum mechanic nature of the qubit, that it can be 0 and 1 at the same time, and that is so-called superposition. And to describe these states that is in between, we can generalize it and to show a little bit of math. So any quantum state can be encoded as 0 plus 1 with some coefficient. And then when we do a measurement, that's what you do to try to tell the state of a qubit. Then you will see that if a quantum state looks like this, alpha 0 plus beta 1, then the measurement outcome will be 0 with a probability of alpha square and 1 with probability beta square. And alpha square and plus beta square has to be 1 because everything has to sum up to be 100%. So if you have a superposition of in the equator, like in Singapore where I'm now, then you have an equal probability of 0 and 1. So you have 50% chance of measuring 0 and 50% chance of 1. So this is the first important principle of quantum computing, superposition. And then as we scale up this analogy to 2 qubits, then there's another principle of quantum computing comes in, that in addition to superposition, we can also have something called entanglement. And entanglement means that, for example, these 2 qubits, they can be strongly correlated. While in a classical sense, all the bits are independent. They don't really relate to each other. But using a quantum computer, and if you have a state that is called entangled state, for this example, a very famous entangled state called Bell state, that you have 1 over square root of 2, 0, 0, 0 plus 1, 1. Then when you do the measurement, as I explained in the previous slide, then you have 50% chance of measuring 0, 0 and 50% chance of 1, 1. This means that you will only see 0, 0 and 1, 1. So when you have the first qubit 0, the second one is always 0. When you measure the first one is 1, the second one is always 1. So they're always the same. And this is no matter how far you separate apart. And this entanglement is an intrinsic property of this quantum state, that they can be strongly correlated. And of course, the quantum state is general. So it can also be non-entangled like this. So in this example, you measure all these 4 different outcomes with 25% chance. So this is the non-entangled state, and this is the entangled state. So here is to tell you about the entanglement, the second principle or weirdness of the quantum computers compared to classical computers. And then if you look at this non-entangled states, previously I have this coefficient or plus. Actually, they're all complex number, and it can be negative as well. So if you change this coefficient to negative, actually you bring up the third principle that makes quantum computer powerful or weird. It's called interference. So this is a bit like maybe you think about a wave on the water. When you throw 2 stones in the pond, so there will be wave. And when the wave meets, there will be interference. So if you have 2 strong waves meet together, they might get enhanced. Or if you have a high wave and low wave meet together, they will cancel out. So in this analogy, you can see that in quantum computing, we can use this interference between these different outcomes. We can, using the interference to increase the probability of getting the right answer. And then also using the destruction interference to decrease the chance of getting a wrong one. So here's an illustration of one of the very famous algorithm called Grover's search algorithm. So this algorithm doing some kind of like database search. So here I show you a very simple database. For example, we only have 3 bits. So that means we have 8 different outcomes. So we have 0, 0, 0, 0, 0, 1, and 1, 1, 1. And we are looking for 0, 1, 0. And you can see that in the x-axis is showing the different entries of the database. On the y-axis is the probability amplitude, which are the alpha and beta that I've told you about. So this could be a positive or negative number. So to start with, it's actually very common in quantum algorithm. So you first generate superposition of everything possible. And so using the first principle, superposition. So you actually generate all possible solutions. And then you can navigate and try all these possible solutions kind of like at the same time. So to parallel it. So using this Grover's algorithm, if you move to the next step, you actually can mark the correct answer using a negative amplitude. And then one more iteration, you can actually enhance the probability of finding this. So if you do a correct number of iterations, you can increase the probability of getting the right answer to be very close to 100%. And at this moment, you do a measurement, then you have a very high probability of finding this correct answer. So in just a few slides, I told you actually 4 things. I told you about superposition, I told you about entanglement, I told you about interference, and I also mentioned about measurement. And the measurement is very important because actually in quantum computers, everything is probabilistic. So actually when you do a measurement, you need to do many times and trying to sample the quantum circuit and try to get the right answer. That's why in the Grover search, you're trying to do correct number of iterations to enhance the number of chances to get a correct answer. So this is a very quick introduction of the 4 principles of quantum computing. And then another thing you probably heard is about the power of quantum computing, why we care about quantum computing, even though now we have very powerful classical computers like the IBM Summit supercomputers. The thing is that even though with these very powerful computers, we still have a lot of problems that we cannot solve. For example, to simulate very complex molecules like virus or like some organic molecule, caffeine, or other things useful for pharmaceutical use, they are really just out of reach for the traditional supercomputers. And to understand why, you can actually think about how you can use a classical computer to simulate a quantum computer. And in the next few slides, I will demonstrate to you that just for a very small quantum computer, it's already very hard for a classical computer to simulate, which in a way to show that the quantum computer can be more complex and therefore might be able to model even more complex systems like the molecules, or in the talk I show you later, all very complex financial problems. So as I told you earlier in this, that 1 qubit can be described by these 2 quantum states in superposition with 2 coefficients. And if you increase to 2 qubits, you will already have like 4 coefficients, and 3 qubits is 8 coefficients. And each of these coefficients are complex number, which means if you want to describe this quantum state on a classical computer, each one you need to be a floating complex number. If you put 32 bits each, the real part and complex part, there's already a 64-bit number. And then the number of this complex number required would be 2 to the power of n of the qubits. So very quickly, if you scale it up, it already goes to a very, very big number that will be out of reach of any hardware storage or RAM that we have available. In fact, just by 275 qubits, you already require more number of atoms in the observable universe. And usually when we use it on a classical computer, we use transistor to store, and 1 transistor may be storing 1 bit. And so that is just showing you that just by having a quantum computer with about 300 qubits, there's already completely out of reach of a classical computer forever. So actually in the current status, I think most powerful supercomputer can simulate a quantum computer maybe about 50 qubits. So that is really showing you that the growth or the scaling of a quantum computer is really different from classical computer. And that's why we believe that the quantum computer can be very powerful in the future. And now let's talk about how do we program our quantum computers. So in a classical computer, maybe you have learned in your computer science class or introduction to programming that the classical computer in the most basic level is in operating using circuits, logic circuit, like AND or NOT, NAND or XOR, and this we call gates. And in the quantum computer, if you go to a most fundamental level, it can also be described by these quantum circuit models. And the only difference is that the gates are different and they can have this principle I explained to you before. For example, this H gate or Harman gate can generate superposition. And these two is called CNOT gate or control NOT gate that can entangle two qubits together. That's the entanglement. And then these are the measurement part that I told you about measurement. So you can also add some other things that they can help you to interface the different qubit and different state together. And you can have these Grover's algorithms. So in IBM, we have an open source Python framework called Qiskit, and which I'm going to show you in a short moment to how to use that to demo. So using this language, Python language, you can already just very simply import a quantum circuit, and then you can construct a quantum circuit. And the quantum circuit looks just like this, same as the schematic shown here. So 5 years ago, IBM put the first quantum computer on the cloud. And then this is an animation to show you how we actually do it if you run the program on your local computer and send a quantum program through the cloud, and then go to our IBM Quantum Center. We have these more than 20 quantum systems, and you send a job to there, you queue, and then you send to a computer and calculation and return back to your computer. So this is a cloud-based quantum computer that really enable access of quantum computer to everyone. Because before IBM put a quantum computer on the cloud, only people that have access to a research lab, like what I did in my PhD, only those people or researchers can have access to this. But now anyone, like including yourself, in a very short minute, you can register accounts and then create a program, and you can already run a program on the quantum computer. So this is to show you about how a quantum computer looks like. So usually you see a very big photo and with a cylinder like this. If you open it up, it may look like what I show you my profile photo in the first slide in my introduction. And there will be many layers, like we call chandelier, like the lights. But at the very bottom is actually the quantum computer or the quantum chip. And it's actually pretty big compared to the transistors. So these things are in millimeter scale. So you can see these are optical chips. If you zoom in, this is a 1, 2, 3, 4, 5, 6, I think 6 qubit or 8 qubit chip. So so this is how the qubit looks like, and we use superconducting materials to make the superconducting qubits. That's why we need to cool down to a very low temperature, 50 millikelvin, which is minus 273.15 degrees Celsius, extremely cold, almost absolute zero. So yeah, so that's the introduction of the quantum computing, and I'm going to quickly switch over and show you a demo of how to run a quantum program on the cloud. So hopefully you can see my browser. So if you go to quantum-computing.ibm.com, you'll be able to register account, and then after register, you go into this account. And I'm going to show you two different ways. So we have two things. One is called IBM Quantum Composer. The other one is IBM Quantum Lab. The Quantum Composer is a visual circuit composer that you can drag and drop and just to compose a circuit. And it's an extremely simple circuit way to compose. So it's great for teaching. So I can just quickly do one. And for example, I put Harman gates. So you can see that now we have 2 qubits. And you can see here we have a probability distribution of 50%, 0, 0, 50%, 0, 1. If I put an entanglement gate, like the Bell state, entangle state I show you, you have entanglement of 0, 0, and 1, 1. So you only have these two outcomes. without 0 and 1, 1. And then we do a measurement. And I can do a setup and run on a real computer. So if you are an open user, so you have access to about 10 quantum computers. So we can choose, let's choose one that's a bit less busy. Example, maybe this one. So you can just set it up, and this is the number of shot means how many times we run this. As I explained to you that the quantum computers are probabilistic, so you need to run many times to actually sample the distribution. So we run 1,000 times, so you can just click it. And in a few minutes, depending on the queue, we already send the quantum computer and it might return the result in just 1-2 minutes. So this is an extremely simple way of constructing a circuit. So while we are waiting for this, I just want to quickly show you how we can run this similar thing using Python, because this is a circuit composer just for learning and teaching. If you want to make any complicated program, you should use a Python-based, Jupyter Notebook-based environment or pure Python script. So if you go to IBM Quantum Lab from here, you open a Jupyter Notebook and import some basic things that you will need to use for sending the jobs. So I can just create a circuit that's the same as what I composed there. So maybe I zoom in a little bit. So what I did here is I have a quantum circuit with the Hadamard gate and the CNOT gate. So I can do a quantum circuit equal quantum circuit, and I can tell that I have two qubits, and so I can already see how it looks like. So now I don't have anything, so it's empty. But if I compose, I add one Hadamard gate, you just add one Hadamard gate. If I add another CNOT gate, and the CNOT gate is 2 qubit gates, so I need to put 2 index. And so this is how you add the Hadamard gate and CNOT gate. And at last, we just need to do a measurement. So we already make the same circuit here. And so to send a job, we just need to first, we have a provider equals to, I think we already have a provider. So we have a provider and we need to find a quantum computer. So let's do a provider get backend. And we can find maybe the same one, which is IBM Q Lima. So let's just see. So we get a backend that is IBM Q Lima, that is a 5 qubit quantum computer. And we already have the quantum circuit, so you can just do something like this. Quantum execute, quantum job backend equals backend short equals to 1020. So hopefully if this is correct. Okay, I need to import this. So it does exactly the same thing I did in the composer. You just send a job to IBM Q Lima. So we can go back and see how the job looks like. So as you can see that similar to the simulator, we get about 50% of 00 and 50% of 11. But different from the simulator is that we actually get 01 and 10, which is what I will tell you. Because in the near-term quantum computer, they are not perfect. They have a lot of noise. So there's some bits of the information is flipped from 00 to 01 and maybe the 10. So these are the challenges that I will tell you more detail later, that how we can tackle them and how to improve the quantum computer so that we can do more reliable calculations and yeah, solve real life problems, such as the problem in the finance sector. Okay, so that is the introduction to quantum computers, and I already spent 25 minutes, so I need to speed up a little bit in the second part. So hopefully you see my slide again. So as I told you, 5 years ago in May 2016, IBM Quantum put the first quantum computer on the cloud. And since then, we have over 360,000 users, and we all run all together, all the users. We run 1.1 trillion quantum circuits in total. And every day we have more than 2 billion circuits running on our quantum systems, and we have 25 quantum computers available on the cloud. And all the users and our collaborators written over 700 scientific papers. So this really shows that how putting a quantum computer on the cloud really accelerate research and discovery, and also help everyone to just have a hands-on to real quantum computer and try things out. And we also have IBM Quantum Network, which have our partners and hubs and members. We also have staff member and academic members. And I highlighted a few that is in the region. They're all based in Singapore. So Entropica Labs and Horizon Quantum Computing are quantum startups in Singapore. And we also have academic partner is National University of Singapore, where also I did my PhD. So yes, so let's move on the real thing that you came here to talk about. So let's see, there's no question yet. So if you have any question, just post on Slido and I'll try to answer at the end of this. So we can move on to finance. So in IBM Quantum, we see solving problem in finance. We can roughly divide into 3 different class of problems in finance sector. So namely, machine learning, optimization, and simulation, which I will also touch upon in these 3 different areas. So first is machine learning. So machine learning problem can be used, for example, for fraud detection, credit risk rating, customer segmentation. And here is a machine learning model called support vector machine, which is used in classical machine learning. And I'll show you how this can be, quantum computer can be used to improve the support vector machine. So a quick introduction to a support vector machine is, for example, you have some samples have different features, maybe a picture of cats and dogs, and they have some features like maybe tail length or the hair. So you can take all these features and then you have values for these features, and you can put all this into a map, a feature map. Here is a 2-dimensional feature map, and so the dots of your samples will be gathered in different clusters. And the support vector machine model is trying to find a hyperplane that can maximize the margin and separate these 2 clusters. So this is a basic idea of support vector machine. But what if the data is not linearly separable like this, that we cannot find a hyperplane that can just do a cart and separate these 2 clusters? So this is similar thing, but in 1-dimensional. And to solve this problem, we could apply a feature map or kernel that transform a lower dimensional feature space to a higher dimensional feature space. And because of these additional dimensions, we can now find a hyperplane that can separate these two clusters. And what quantum computers can do is to create a quantum feature map that can be applied to support vector machine, and then hopefully can do a better job than classical machine learning to have a higher accuracy. And these quantum feature maps is actually can be expressed for a parameterized quantum circuit, like the quantum circuit that I show you in the demo. But this circuit have some parameters in it. So you can see this P, they have some phase rotation, have some parameters, and these parameters can be changed and can be improved and optimized to get better ones. I see a message. Okay. Yeah. If you have any question, you can post on the chat or Q&A section. So so this quantum circuit can be used to generate a feature map with some parameters. And we did this in 2 years ago and demonstrated in the real quantum computers. And so it's just like this that we computed a quantum feature map and transform this data to a high dimensional, and we find a support vector that can actually separate data very well. And these are the data and how we can classify them. And this data, when we did it at that time 2 years ago, this data was artificial and just to use to demonstrate that at least there's some advantage towards using quantum machine learning compared to classical machine learning. So that was by proving by practice. But later last year, we have a very rigorous proof that support vector machine with a quantum feature map can actually achieve quantum advantage, meaning that a quantum computer can calculate better or more efficient than a classical computer for some problems using this support vector machine with a quantum feature map. So when can we expect a quantum advantage using a quantum machine learning? So here are a few different quantum machine models. I only mentioned about quantum support vector machine, but there's also quantum neural network or these quantum Boltzmann machines. The good thing about them is they're near-term compatible, meaning as I showed you in the demo, that you actually see errors in the near-term quantum computers. So because now the quantum computers are still small scale, so they have errors, and we need more qubits, then you can do something called error correction. Actually, this is not new to quantum computer. It's a bit also applied in classical computers that, for example, you have a transmission through a network. Maybe now you're watching Zoom, I think the video stream actually do a lot of error correction to make sure the information transmitting from me to you are actually correct. So, but it goes through all the networks like cable or even from the space or radio wave. And a lot of things can actually create errors. So there's some algorithm that you can do to detect the errors and then know what went wrong, and then try to correct back to preserve the errors. So something similar can be done for quantum computers. But to do that, you need actually qubits are low error rate enough, and also we need a lot more, because to do error correction, we actually have an overhead. So for example, maybe we want to have one very good logical qubit, we may need 1,000. That is the normal qubit, physical qubit. So right now we are still below 100. So this can take a few years to achieve. But the good thing about these three algorithms, maybe I can go back, is, so if you don't have error correction, which means that the quantum circuit we run have to be very short. So if you don't have error correction, the quantum computation can only happen within 100 microseconds, so very short time. So what you should do is have a very short quantum circuit like this one. So something that you can see just one screen is pretty short. And so that means you can run without generating too much error in the quantum computers. And then so you can extract some information at the end. So as you probably, I will show you in the next two problem class, these are a very common theme of the algorithm we use called near-term compatible, is to have very short circuit. And then we have a classical and quantum hybrid nature of this. So you have very short quantum computation and then get a result of classical computer. Using classical computer, optimize the circuit and then feedback, because this circuit have parameters, back to the quantum circuit, and then you run a better result. And then you have this iteration loop to improve the circuit and get better results. So we believe that machine learning or quantum computing can bring quantum advantage is because there's a lot of problem very difficult to scale. And it's very hard for classical computer to simulate quantum computer, a circuit with more than 50 qubits. So we think that the first quantum advantage can be achieved with just about 100 qubits. But the keyword here is really you need to have a sufficient quality, which what is sufficient is unclear, but current days qubits are not good enough. So you see that we'll need to actually scale the number of qubits, but also improving the quality. And the question is whether the first quantum advantage will be machine learning. Maybe. We are not certain, but just like classical machine learning, a lot of machine learning algorithms are heuristic, meaning that there's no rigorous mathematical proof that it's better, but you demonstrate by doing it, by actually running and solving the program, and showing that it's better. And that is when you show that we have advantage. And we hope that we can do this in the next few years. So in Qiskit, we also have a very dedicated Qiskit machine learning application modules. And this application module here is architecture. And you can see that it builds on some fundamental building blocks, like the quantum kernel or the feature map that I mentioned. Something I didn't talk about is the quantum neural network. So it also build basic building blocks. You have different kinds of quantum neural networks as the building block of the algorithm. And then we have the built-in algorithm that using these building blocks to do classification and regression. And we also make this very modular, and also since it's based on Python, we leverage on the Python ecosystem for classical machine learning. So we have very easy integration with PyTorch via these torch connectors, so that you can really integrate Qiskit machine learning with your existing machine learning algorithms and try to just plug in, and you can already solve this, or to at least play with at the moment using quantum machine learning. So if you want to know more about machine learning, you can go to this link and Qiskit.org documentation machine learning tutorials, or you search Qiskit machine learning, you should probably be able to find this. And you can see a different kind of tutorial demonstrating this different feature of Qiskit machine learning, not just for finance application, but more general. Okay, so let's move on to optimization. It's the second class of problem that we think in quantum computer can help in finance. And the optimization problem usually can be formulated in a problem model called quadratic unconstrained binary optimization, or QUBO for short. So this problem formulation is for binary decision variable, meaning that they are just 0 or 1 or true or false. And they only contain linear equality constraints, but we have these quadratic penalty terms. And this problem can cover many NP complete, very hard problems. For example, in finance, portfolio management or optimal feature selections. So here's a illustration to explain about portfolio optimization. So we want to choose a portfolio of stocks and try to make sure that we can get the most outcome given a risk appetite you have. So here's a chart. On the x-axis is showing the risk, or how much risk or volatility of the stocks, and or how much risk that you can be willing to take. And for given risk, there's a highest expected return, and then there will be an efficient frontier showing that for this surface of the highest return for given risk. And the problem is to try to find the portfolio that lie on this efficient frontier, the best combination of the portfolio to give you the best outcome, perhaps expected return, giving your risk appetite. So for this problem, quantum computer, we can use this near-term quantum optimization heuristic, very similar to the machine learning algorithm that I told you, because this is really the theme of near-term quantum algorithm, because we still don't have error correction. So the way it does is to formulate this QUBO into a physics problem, and then it can actually model using some algorithm for variational quantum eigensolver. And so the QUBO will be formulated to some called Ising Hamiltonian, and this is like encoding some energy of a spins in electrons. So it's a physics problem, but actually you can map financial problem, the QUBO to this physics problem, and then using quantum computer to lower the energy of this Ising Hamiltonian. And by lowering the energy, you can actually find the optimal combination of the portfolio that you're looking for. So this is how the whole formulation works. So you do this quantum operation Hamiltonian, and you have this wave function, which is encoded by the quantum circuit with parameters. So as I explained earlier, so you have this iteration loop that you try one circuit, you do calculation for quantum computer, you read out, and then based on the outcome, you come up with a new set of parameters, and then you run again. So it's a bit like if you're familiar with the gradient descent in machine learning. So you're trying to optimize the the parameters to get a lower and lower energy state. So this is how it works for this near-term optimization heuristic, or in general quantum algorithm, variational algorithms. So yeah, so exactly here is showing the kind of circuit that you will see for optimization or machine learning. You have a circuit that have contained parameters, and we can change the parameter in each iteration loop, and we're trying to get a better and better answers. And the good thing about this is covariational principle is that the lower the energy you get, you can never get lower than the optimum or the feasible result. So if you get a lower number, you know this is a better answer. You will never go lower than actually a feasible one. So you will not go to a wrong direction in feasible answers. So let's come back to a portfolio optimization, and we formulate this using this mean variance optimization problem. And so here is example of 5 assets in this, and their expected return. And there's also a covariance metric, which to show you the correlation between the stocks. So some stock might be going up at the same time as the other stock, and how strong they correlated can be encoded into covariance. Sometimes it could be also reversed. So the covariance matrix might be negative. So one stock goes up, the other goes down, or vice versa. So we can use formulate this, and then it convert to a quadratic program, and then it can convert to this Ising Hamiltonian and run on quantum computers. And we demonstrate this on a real quantum device. If I think asset is 6, and we can change the budget, meaning how many assets you want to put into this portfolio. So, and then this is to calculate the efficient frontier for each given risk and different number of budgets, different number of assets in this portfolio. So similar to the Qiskit machine learning, we also have a dedicated Qiskit optimization module, and to solve a general optimization problem, but also we can solve for financial optimization problems. And very similar to machine learning, we also have a very easy integration to a classical optimization library called Cplex, do Cplex. And you can form, this is a very traditional, very well known software in the optimization community. And you can solve the problem that is formulated in this quadratic program, like the Kubo I show you. And below is the different solver, the quantum solver, Kubo, and classical solver is also available, so that you can do some benchmarking and compare to the quantum algorithm used. So, and you can run it on a quantum simulator or a quantum hardware. So I'm running a bit out of time, so I'm not sure I would do this demo. So maybe I'll move on to the third part, and if we have time, we will do the demo. So when do we expect a quantum advantage? So for this optimization problem, you usually have like 1-to-1 relation between the number of binary variables and the number of qubits. And here is a classical benchmarking library to show you which problems are easy and which problem are hard, or which problem are really open, meaning that we don't know the answer with, in terms of the number of variables. And easy means that something that you can solve using your laptop in an hour or so. Hard is something that you can maybe you need to compute using a supercomputer or a cluster. And open is something that really even the most powerful classical computer may not be able to solve. And we can see that we will need to reach, for quantum computer to bring an advantage, we should at least solve problem that is having a variable of 10,000. And if we think about this 1-to-1 relations between the variables and qubits, that means that we at least need to have a quantum computer that have around 10,000 qubits, and probably also need to have efficient qualities. So so we expect that the quantum advantage for optimization would be probably later than machine learning, because machine learning algorithm usually require lower number of qubits. But at least the near-term algorithms, they are compatible to near-term because these are iterations. So near-term, even without regression, we can run it. the best thing about this is similar to machine learning heuristic. We don't have a rigorous proof that they are better in theory, but we can demonstrate when the hardware is ready, we run it, we actually show that there's advantage. Then even as you all know, the finance market is really huge, have a strong average leverage. Even a small improvement can have a huge return in the value. So that's why a lot of banks are actually working with us in IBM Quantum to try to study solving problems using quantum computer. So the last part is about simulation. So we can do option pricing using quantum computers. And option pricing here is the most simple model option pricing for European option call option, and which means that you have just one stock, and then you are trying to one asset, and then you can buy something now for price, and it has a fixed maturity date, maybe, I don't know. I think you've already known that maybe 90 days or 1 year. And then you have this price that you buy called strike price now. And then, so the problem is that you try to estimate at a maturity, what would be the expected price at the time called spot price. And of course, you want to earn money as an investor. So the spot price, the actual or the estimated price at maturity, it's better to be higher than your strike price, the price you actually buy the thing. So, so if you have this formulation and spot price is, you need to simulate, and classically usually using Monte Carlo simulation to have different scenarios, and then you have a distribution of the spot price based on different scenarios. So you have a distribution, and then you try to really find a scenario that you actually can, you need to know at mean that you're actually earning money. So the spot price should be higher than the strike price. And you can do this option pricing and to determine whether you want to buy this option or not. So you can do this thing using quantum computer. And this is what JP Morgan Chase is working with IBM. And this is the circuit they use for European derivative pricing circuit. And again, it's very similar to the circuit I showed you in the two different class, because this is really the theme for near-term quantum computers. They are very short. They are a lot of parameters. They have small number of qubits. Here it's only 3 qubits. But just using this simple circuit, we can already demonstrate some solving some simple problem and demonstrate that at least for this simple problem that the quantum computer can solve them. And we also hope that the scaling of this algorithm can be better than classical computer, and in the next few years we can demonstrate the actual advantage. And how do we do the stochastic modeling using qubits? So stochastic modeling, traditionally, you can basically you have like a good outcome and a bad outcome, and you just have some probabilities, and you can encode this probability into qubits and into this amplitude that I told you in the introduction slide. So you can encode to like how much chances it can be measured to 0, how much chances it can be measured to 1. And then what you want to do, encode in the qubits, and then what you want to know is how to estimate these numbers. Because as I explained, the quantum computers are probabilistic. You need to do measurement and you need to sample them. But when you sample them, you actually collapse the quantum circuit and you could change the quantum state. So you need to find an algorithm that actually extract this amplitude information without destroying the quantum information. So this is an algorithm called quantum amplitude estimation to extract this amplitude information so that we can encode this stochastic model of this option price to this quantum computer so that we can try to solve it. So this is a classical way, canonical quantum amplitude estimation. Okay, we'll end in 10 minutes, so I got to accelerate so that you have time for questions. So this is a classical way of solving, and it was discovered in 2000. But the problem is that you actually need a lot of circuits. And if I put it more in a box, you see the actual simulation is here. And the top is actually what you're trying to extract this information. And this is an extra thing that you need to have overhead. So it requires much more qubits and also many more gates. So for near-term quantum computer, it would be very hard to achieve. But in the last 2 years, we have made a very big advancement in this field and trying to improve this algorithm. Our collaborators in Mitsubishi Bank in Japan and collaborate with IBM Research in Tokyo. They find out that you don't actually need this overhead. You can just focus on this one, so significantly reduce the number of quantum qubits and the gates. The problem is that it doesn't have a rigorous theory to prove. So, but very quickly we improve. Scott Aronson and the collaborator from US improve this. You have a rigorous theory, but have a last very constant. So, and then very quickly in a few months from IBM Research Zurich, we improve this even further, and we have good performance. We have simple circuit, and we also have a rigorous theory to back this algorithm. So now with this one, we can actually show that this is the, and this blue line is for Monte Carlo simulation. You can see the estimation error and scaling with the number of samples. So you see the scaling is worse. That means if you want to lower the estimation error, you need to scale the number of sample much more. So for a given error rate, for example, 10 to the minus 8, for the Monte Carlo, you need 10 to the power 16 samples order to code when you run the algorithms. So for the canonical, like the traditional amplitude estimation, you need even higher. But with the recent advancement, we reduced this extremely more efficient. So we hope that in the near future, we can use this improved quantum amplitude estimation algorithm to solve these problems. And we also have a Qiskit finance module dedicated to finance and leveraging on the Qiskit optimization and Qiskit machine learning. So you can have a look in this tutorial. Unfortunately, I don't have time to do your demo for this, but you can go there and take a look that show you portfolio optimization, pricing, European core options, and different other things, also Asian barrier spread pricing and credit risk analysis, and also using machine learning to do option pricing using QGANs. Okay, so yeah, very briefly touching upon the advantage similar to the previous one. So what we can see, this is actually require even more because the circuit actually is much deeper. You need a lot more depth, not a shallow circuit. So we actually will need a quantum error correction. And for that, we will need much better qubit and many more qubit because the overhead for error correction can be 1 to 1,000. So the last part I would want to touch upon is the technical challenges, which I already mentioned many times when I talk about applications. So one thing we have is about the input and output problem. So we say that quantum computer can encode a much higher dimension of things, but the input and output are still limited by classical. So we will need to find a way to how to encode using just the input that is smaller dimension like our classical computer, and the output also, to actually can instruct a quantum computer and leverage on this large dimensional space and to do the computation for us and read out what we are useful for. So this is a general problem that we quantum algorithm developer have to think about. And then the errors is another very big problems, and the errors come from many different ways, and IBM come up with a metric called quantum volume, which is a single number benchmarking to show that the performance of the whole system, including the hardware and software. And I can show you, this is a very encouraging slide that we see an analogy of the Morse law in classical computer, that the number of transistors scale doubling every 18 months or so. So for the quantum volume to measure the performance of quantum computers, we actually see even better scaling. Then they don't just double every year, but exceeding this. So we hopefully in the next few years, we can see a really exponential kind of growth and to see a much better quantum system with bigger number of qubits, lower errors. And this is our hardware roadmap to try to scale the number of qubits. So now we already have 65 qubits. Later this year, we have 127 qubits. And in the next 2 years, we're trying to scale to 1,000 qubits. And we hope in 2023, this system is big enough that we can do error correction. So we can at least encode to 1 logical qubit. And then in the next remaining of decade, we can scale it further to even up to 1 million qubits. And hopefully by then we can demonstrate a lot of a problem that has quantum advantage. And similar to the hardware roadmap, we also have a software roadmap. And so you see, as the system scaling up, our software also matures. At first we have only kernel developer, people that need to know the quantum circuit. But as the field matures, then we don't need people that know quantum circuit. Just like in the classical computing, now you don't actually need to know how a number is stored in a transistor. You just run a library and you call the library APIs. So we hope that in the next few years we can also achieve this. Again, in 2023, you hope with this quantum system to be ready to be error correction. We also hope the software can be really ready and we have a frictionless development, so they can integrate to your existing workflow to solve problem. A bit like maybe using GPU to accelerate your some software machine learning or something like this. We use a QPU to accelerate as part of the workflow and integrating to your classical computing architecture. So the things I have touched upon are actually all covered in this paper, so you can read. I think it's open access, so you can read more detail on this, and it's also formulated in these 3 problem class. And at last, I just want to advertise one event called IBM Quantum Challenge 4, and this is happening right now. It just launched yesterday, and this challenge actually cover all the application module I show you: Qiskit finance, Qiskit machine learning, Qiskit optimization. In addition, we also have a chemistry problem, Qiskit nature. So if you join this, you will be able to do hands-on and tackle some real-life problem we formulated using Qiskit application module. And you can learn this thing that I talked to you about today. So I hope that you can register and I'll see you there. Okay. Okay, so we will be extending the session for 15 minutes for Q&A. Okay, that's good. Yeah, sure. Is there any questions? Let me try to see the slide of Q&A. All right. So I see a few questions. If you have more questions, you can just keep it there on the Slido, and I'm trying to answer. So the core question is, does quantum computing have the ability or potential to hack into blockchain systems in the future? If yes, is there a way to prevent it, like firewall or etc.? Okay, that's a very quick question, and I think it's quite a common concern. I don't know that much about blockchains, but people do worry about another thing for also what make quantum computer very famous, called cracking the cryptography. So in 1994, there was an algorithm called Shor's algorithm, and Peter Shor demonstrated that using a quantum computer can potentially crack a very well-used algorithm, cryptography algorithm called ISA algorithm, which is widely used for encoding very secret information like the credit card information. And so indeed, theoretically it's possible, but as I show you, there's a lot of technical challenges for quantum computers. And so to be achieving the Shor's algorithm, we might need a quantum computer that is 1 million qubits or even more. So there's different estimates. And so I think the common consensus is that maybe in 20 or 30 years time, quantum computer might be able to threaten this. So I don't know about blockchain that much, but maybe it will be similar time horizon. So that might be able, maybe quantum computer will be threatening that. So yeah, so maybe that would be a problem, but not in such a near term. So those are still very hard problem, and hopefully still stay for a while. And if there's a problem, the good thing is that actually a quantum computer also brings a quantum encryption that is safe for attack from quantum computers, that you can using entanglement or superposition to do a safer encryption. So you can also do that. And in fact, IBM also have this quantum cryptography works on it. Yeah. So sorry, I don't know about blockchain, so I couldn't answer specifically for that. But in general, it could be a threat, but the horizon probably would be very far away. Okay. Second question, how did you even start your career in quantum computing space? Is there any space for non-engineers or coders? Yes, that's an excellent question. So you see my background is like experimental physics, and it looks like I know quantum computing a lot, but the way that I got into IBM was not about this. It was about the games. So now my job is not doing research, and I actually do more like these educational things. And the way I get into IBM Quantum was because I joined a hackathon and I make a game that teaches quantum computing. So I think actually there's a lot of opportunities, just like any industry. Actually, it's just not where most people, when you look at quantum computing industry, you see the researchers, you see the developers, you see the coders and everyone. But actually, there's so many people like what I'm doing now. It doesn't necessarily have to be those very hardcore code. If you like showing something demo and this thing, you can also do a job. And actually, it has also other people like marketing or human resources. All these people are needed in the quantum industry. So there's many ways to get into it. But I think a good way to get into it is at least demonstrate that your interest in this. So you could be doing your current job, but in the different industry. But to get a job in the quantum industry, it might be good to show your interest. And to show your interest, I will advertise this again. You can join like some events, like hackathon or this quantum challenge. You do it and show it, and you show that you have participated in this to demonstrate that your interest in the industry is for months or for 1-2 years. Then when you apply for a job in those, then you also know the ecosystem, you kind of know the problem. Then I think we can enhance your chance of getting hired in the industry. Okay, so next question. Is there any off-the-shelf programs or powered by quantum computers solving everyday problem in finance? Okay, so this is the excellent question about this. So we don't currently have this. So this is what we aim to have in 2023, to have built quantum runtimes that will have existing all the program to be solving certain type of problem, maybe corporate optimization. So that even you don't need to be very technical, just need to know how to formulate your problem and then translate to the language or the parameters to be setting this pre-built quantum runtime. And then hopefully you can solve the problem in finance. So that will be coming pretty soon. Okay, one question. Can P vs MP be solved with quantum computing? I'm not sure what that means. I'm trying to show prove that whether quantum computer can break this MP hard boundary. If you can, elaborate on the question would be better. Okay. How long is a few years before we see application of computation in finance? So yeah, nobody can tell you a concrete answer because there's quite a lot of unknowns, and it could be long, it could be short, and sometimes there's surprises in development that actually speed up, like the algorithm that I show you in here, the quantum amplitude estimation. So from this to here, all it takes is some researcher's genius, and he already reduced the thing by 10 to the power of 6, a million times easier to do it. So there's nothing prevent us that tomorrow suddenly someone bring it to 10 to the power of 4 or 10 to the power of 2. Then maybe suddenly next year or tomorrow can achieve on the quantum computers. So quantum computing still have a lot of like researchy feeling onto it, that a lot of things are still really heavily in research and trying to change and improve. And in the hardware, there's also have breakthroughs. For example, recently we improved the coherence time, which showing how long the quantum information lasts in the system by a few times. And that improved the fidelity, and that will actually improve how many, when we can do the error correction and how many overhead we will have. Then that will also speed up when we can apply the quantum computer in actual business operations of finance industry. So the question is no, but we hope that this decade will be a quantum decade. And in fact, we have a playbook that you can download. If you search a quantum decade IBM, probably you can find. They include a lot of information, high level information of what we see in IBM Quantum as the thing that we can solve using quantum computer, hopefully in this decade, to show quantum advantage. Okay, we'll end in 10 minutes. I actually don't see many more questions. This is the last one. If there's any question, please leave the chat, leave it in the Q&A session. So does that mean the entangle state will proliferate through all the qubits? Not sure what that means. So in the entangle qubit means depends on how many CNOT gates you put, or for example here also. This is also kind of entangling operations. So depending on the control node and how much part of the qubit you're controlling, so you will be entangling these two. It's not necessarily entangle everything together, but this is also one thing that the error might brings the thing. So if you have a big system like this that we are trying to build, 1,000. So this CNOT gate may not be able to directly apply to each one. So we actually need to have a software layer in between to translate the ideal circuit to the actual circuit. And if so, I don't know whether I have, maybe here is all right. So if you see this, each node actually is a 1 qubit and the edge are actual connection, and that is showing, maybe I can switch over to here. Okay, yeah, there's some question in the idea tab. Okay, I'll look at it. So now I'm just showing you, example, we have this system, 27 qubit, quantum volume 128. So you see that these are the qubit indexes and there's connection in between them. So if you want to do a CNOT gate between 0 and 8, for example, you can't really do directly because of the hardware, how it's constructed. So you can do something called swap gates, and you can swap them. But the swap gate actually generate a lot more gates, and because of the error of the gates, you actually generate more error. So you could actually make it harder to run a program if you want to entangle everything. So that's another challenge. So the system need to be really good to be able to run extra circuit if you want to entangle everything. So I want to show you, here is a simple example so we can direct. But if you have more complicated examples, so the ideal circuit would be this, and it actually decomposes and it will generate more gates. Yeah. Okay. Let me see the other questions. Ideas. What is the best quantum PC available in Malaysia market? There is no personal quantum computer yet, but as I told you, you can register in this quantum-computing.ibm.com. You can register account and you can already access to, I think, 6 or 7 systems that are small and they are free to use. And you can just try your things, just like I did in the demo. What real world problem have already been solved by a quantum computer? What problem could probably solve in the near term? Yeah, so this is similar to the question about when we can do it. So there's a real world problem that we try to model and try to experiment in a smaller scale and try it run on a computer. But today there's no actual problem that a quantum computer can solve that classical computer cannot solve. So we are still not in the quantum advantage era. So we hope that again in the next few years, we will be able to achieve this. And we have reasons to believe this because the problem of scaling, that there's a hard problem that scale very fast in a classical computer, but not in a quantum computers. And also you see the advancement of quantum hardware and software, just we have seen in the last 5 years. You can already see that all this development will bring down, and also the algorithm development will bring down the requirement to run and solve this problem. So in both directions, we're actually improving the hardware and then also reducing the hardware requirement. So hopefully at some point it will meet, then we can start demonstrating the problem that can be solved, that cannot be solved by quantum computer, cannot be solved by classical computer. And how easily can quantum computing be used by business? Do we need to learn how to use this? Okay. Yeah, so this slide is again the great thing. So you can see the timeline we want to see. So as in the past, like I say, before we put a quantum computer on the cloud, only people researcher can use. But now we have this open software and Qiskit that everyone can download and use, and also the IBM quantum system on the cloud that anyone can register and use and send to real quantum computers. So with this, you can already try it. But now we are still in the era that we want to know about all these basics, like how the qubits look like, how to build a circuit, how each circuit, how each qubit, how they behave, because we are still in a very early stage of quantum computing. Probably in the classical computing at the early age, that you do a programming, you also need a programmer, very low level. You need to know the address of each memory or transistor, and try to efficiently use those things. You need to do a lot of tricks. But hopefully, in the next few years, we can build more advanced hardware and software. And in fact, this year we will have a Qiskit runtime, which package this variational quantum algorithm that I told you that have this iteration, classical and quantum hybrid. And in the traditional model, the classical computer is my laptop, for example, and the computer is on the cloud, quantum computer on the cloud. So you need to, this have a lot of iteration, for example, 100, and you actually need to send 100 jobs. And each job you need to queue because there's other people want to use the computer. So you need to send a job to IBM Cloud, and then IBM Cloud queues and send to quantum computers. And each job maybe take a few minutes, and 100 iteration will be a few hundred minutes. But with the Qiskit runtime, actually, it's a containerized thing. So you can just send a job, and this whole iteration thing is actually in the IBM Cloud. So all the iteration happen from IBM Cloud classical computer to IBM Cloud quantum computer. So it will be a continuous iteration thing. So actually, we at least demonstrate 5 times speed up of using Qiskit runtime. So we hope that by developing this application module and all the other things, then you might not need to know as much about quantum computer to start using it. So that's what we call frictionless development. We try to lower the barrier of entry, and also hope that you can integrate to your existing software infrastructure. Okay. I don't see any more questions or ideas. Okay, we have, I think, 2 more minutes. If you have any burning question, please ask in the Slido. I'll try to answer. Yeah. If not, I really strongly encourage you to try this. I think it will be a great hands-on experience, and it's lasting for 10 days. And we have great support. If you don't know anything yet, so if you register, you see that there's a Slack channel, and there's a lot of beginner every time. So actually, every time we have like over 1,000 people participate, and you will learn from each other. You will learn. We have mentors to teach you, to guide you through, even for the most basic question. So we have 4 challenges. Challenge 1 focus on finance. And actually, it's the easiest. So I think I encourage you to try it. And that is about portfolio optimization. So if you hear what I told you today and you're interested to try and review like hands-on with code, so I think that would be good. So at least you can solve the first one. And the second one is about nature, chemistry. Third one is about machine learning. The fourth one is about optimization. So yeah, I really hope that you can register and participate. Okay. So any 1 minute, any more questions? All right, I don't see any questions. Okay. So if there's no questions, I just want to thank everyone for attending for today's session. If you are interested more to find out, you can, I think you Google me, you probably can find me on Twitter or LinkedIn. Join Qiskit Slack. I think you can meet a lot of other people. Join this challenge again, I think. And the organizer also want to send it a reminder to everyone. The next session will be closing the gender wealth gap through Fintech at 2 p.m. today. So just stay tuned and enjoy the rest of the conference. And I hope to keep in touch with you if you follow me on Twitter or connect with through LinkedIn. Thank you very much.